Okay, so have you ever stopped to think about what it actually takes to run something like Netflix or Uber? We're talking about a scale that's just mind-boggling. 1 million requests every single second. It's this massive engineering quest, right? And today, we're going to tackle it head on. But you're about to see it is not as simple as just, buying a bigger computer. And look, this isn't just a fun thought experiment with big numbers. The stakes here are, well, they're sky high. Because at this level, one tiny mistake, a single bad line of code, that's not just a bug. That can cost a company thousands of dollars, instantly. It's like walking a high wire, but there's absolutely no safety net. So let's just let that number sink in for a second. 1 million. That's not per day. It's not even per hour. We're talking about a million different things happening in the time it takes you to snap your fingers. That is the mountain we're about to climb. All right, so where do you even begin with a challenge like this? Well, like any good quest, you start small. We need a baseline, a starting point to see just how big this problem really is. So we're going to kick things off with a piece of hardware that's pretty familiar, but also pretty powerful, a high-end computer, right here on the desk. So our starting line is a Mac Studio. Pretty beefy machine, right? It's got 12 CPU cores, 32 gigs of RAM. We're going to run a super optimized Node.js framework on it just to see what a single, really souped-up machine can do before we even think about going to the cloud. So take a guess. What do you think the number is going to be?
Whoa, 50,000 requests per second. I mean, that's genuinely impressive for a desktop computer. But let's be real, that's only 5% of our goal. That giant gap tells us something really, really important. One machine, it doesn't matter how powerful it is, it's just not going to cut it. We have to go bigger, way bigger.
Okay, so it's time. Time to say goodbye to the local machine and unleash the real beasts of the cloud. We're heading over to Amazon Web Services to rent what is, for all intents and purposes, a supercomputer. I mean, with this kind of raw power, that 1 million requests per second goal, it should be easy, right? Right? And just look at this upgrade. I mean, it is staggering. We're not just doubling things here. We're jumping from 12 CPU cores to 128. We're going from 32 gigs of RAM to 256. And the network speed, we're quintupling it. This isn't a step up. This is a leap into a completely different universe of computing power. Of course, power like this, it doesn't come cheap, not even close. To run this cloud infrastructure, we're talking about $20,000 a month. So yeah, the financial stakes, they just got very, very real. Okay, our supercomputer is warmed up and ready to go. But this is where the real gauntlet begins. See, raw power is one thing, but it's never enough. There are these hidden monsters lurking in the system. They're called bottlenecks, and they will absolutely murder your performance. So it's time to go monster hunting.
So for our first test, we're going to simulate a really common real-world thing, an API that has to send back a pretty decent chunk of data every time you ask for it. We're not just sending a tiny hello world message. We're moving a full 32 kilobytes of JSON with every single request.
And the result? We hit a wall, a hard wall, at just 100,000 requests a second. That's only 10% of our goal. And remember, we're using 128 CPU cores. So we've definitely found our first monster. The big question is, what is it? So here's our first monster. It's a network bottleneck. And what's crazy is, when we looked, the CPUs were just chilling. They were barely even working. The problem was the network. We were trying to shove so much data down the pipe that we completely choked our massive 50 gigabit connection. It's like having a Ferrari engine, but you're stuck on a single-lane country road. We ran out of road, not horsepower. All right, monster number 1 is down. For test number 2, we're going after the usual suspect. I mean, anytime something's slow, everyone blames the database, right? So we're going to try inserting a simple record into an absolute beast of a Postgres database. This thing alone costs thousands of dollars a month to run. Oh, wow. Okay, this result is just shocking. 35,000 requests per second. 35,000. That is actually worse than we got on the Mac Studio back at the beginning. It just goes to show you, writing data to a physical disk, even a super, super fast one, is just brutally slow when you're talking about this kind of scale. And this is where we learn a really hard, really expensive lesson. You can't just throw money at this problem and make it go away. I mean, to even get close to our goal just by scaling up the database, we'd have to spend another $15,000 a month, and it still wouldn't be enough. This is one monster you cannot defeat with a credit card.
Okay, now for our third monster. And this one is the most devious of them all. The task sounds so simple, right? Just read a single random record from a table that has 10 million rows in it. People do this all the time. But at this scale, it's not a task, it's a trap.
And the culprit is this one tiny, innocent-looking command, order by random. Now, for the computer science folks out there, this is what's called a big O of n operation. But what that actually means is, to find just one random row, the database has to look at all 10 million rows, every single time. Imagine trying to find one random page in a library by dumping every single book onto the floor first. That's what we're doing. The whole system just grinds to a complete stop.
So let's recap. We've been smacked down by the network, by slow disks, and by just one bad line of code. So, how in the world do we actually win this thing? Well, we have to completely change how we're thinking about the problem. We need a secret weapon, one that just sidesteps these bottlenecks completely. It's time to start thinking in RAM.
And this is our hero, Redis. Redis is what's known as an in-memory data store. And that one little difference, in memory, is a total game changer. See, instead of writing to a slow physical disk, Redis does everything in your computer's RAM. And RAM is literally thousands of times faster than a disk. This is how we're going to win.
So here's the new game plan. It's actually pretty clever. Step 1, a request comes in, and we write the data instantly to superfast Redis. Step 2, we immediately send a response back to the user that says, yep, got it, all good. And then, and this is the magic part, step 3, a totally separate background process can take its sweet time moving that data over to the slow, permanent database later on. We've basically disconnected the user from the slow part of the system. That's the secret.
Okay, the stage is set. We've found all the monsters, we've got our secret weapon polished and ready to go. This is it, the final showdown. Let's put this new Redis architecture to the ultimate test and see if we can finally break that 1 million request sound barrier.
But wait, there's one last trick up our sleeve. See, even a single Redis instance, as fast as it is, has its limits. It kind of tops out around that 100,000 request mark. So to not just hit our goal, but to shatter it, we need to go one step further. We're going to unleash a whole cluster of 30 Redis instances, all working side by side in perfect harmony.
And there it is, victory. We didn't just meet the goal, we flew right past it, over 1 million requests per second. It took that combination of massive cloud power, yeah, but also a really smart, in-memory architecture to finally make it happen.
So this whole journey, right, from that first 50,000 requests all the way up to over 1 million, it really boils down to one critical question that every single developer has to ask themselves. It's not enough for your code to just work. That's the easy part. The real question is, can it scale?